Thank you, Mr. Chairman, for introducing me, and welcome everyone. Today, I would like to present our paper on the title Passive Chipless Wireless Pressure Sensor based on Dielectric Resonators. And at first, I would like to motivate why should we use passive chipless sensing. At first, for passive, we do not need any battery or any energy source on the sensor side, and for the passive, the chipless means we have no integrated circuits, no diodes, which will operate in our sensor. So if we avoid using batteries and also integrated circuits, it's suitable, this technology, to use in harsh environments where we have, for example, high temperatures, strong vibration, also high accelerations, which we can find, for example, in milling machines, where we have high temperatures at the milling cutter and also high accelerations of the tool. One key parameter in such process is the tool wear, which will directly affect the surface of the working piece where we want to operate. In the lower part, we can see a workpiece when we cutted the surface by using a milling cutter, where we have, or more or less a new milling cutter, where we have no tool wear, and you can see the surface is very smooth and you have no burr on the right and left side here. But if we are reaching the tool life criterion, which defines where we have to exchange our tool, we will get a very rough surface, a huge burr on the left and right side, and the cutting quality decreases. So, and we want to achieve always a very well cutting quality, and therefore we have to predict our tool lifetime of the used or operating tool. Up to now, we are using only the machining time and the cutting speed, but we are not taking into account any uncertainties in the process. So we need some information about the force in the process to adjust the cutting speed, for example, but also this information can then be used to predict the tool lifetime. This will lead us also to a sustainable manufacturing process, and this will also reduce the cost by using the time where we can use the tool. We can really completely exceed the tool lifetime. So in our concept, we want to implement a sensing system in a milling tool, which we can see here on the picture. The milling cutter are here, the workpiece in the lower part on the slide, here in the upper part, the mounting of the tool. And this will be done by an oil pipe system here, for example, which will transfer the force from the milling cutter to our transducer here. And then we will have an horn antenna and a waveguide where we will transmit the signal to our readout system. But we can also imagine that we can scale this system concept to implement more sensors in one tool to also measure the torque and also the force of several cutters. And this can be done by using several transducers at different resonance frequencies. So the transducer will be done by using resonant dielectric resonators, and in the paper we focused only on the transducer, which is a pressure sensor which will transfer the force information to an electrical domain. So after a short introduction, I would like to go to the outline of our presentation. First, I want to present the sensor system, the electrical design, then the mechanical implementation, followed by the characterization, and at the end I would like to summarize the findings in the conclusion. So the sensor will consist of a dielectric resonator here, a reader there, and a broadband signal will be transmitted to our sensor. So the sensor will create a notch by absorbing the energy from the spectrum. And if we manipulate the boundary conditions of our dielectric resonator, we can see a resonance frequency shift, and this can be interpreted as a force information. So here we can see the design of our transducer. We have a waveguide, a dielectric resonator with a certain air gap and the membrane. And in the first step, we investigated the different or several modes which we can use for our designs. For example, if we look at this mode, we have field minima on the surface, so we have more or less no sensitivity. But if we are looking at this mode, for example, we have a high or E field strength on the surface, so we have also high sensitivity, and we can use such modes to measure the force. So in this graph, you can see full wave simulation results where we can see strong frequency shift over small membrane deflection, roughly 1.2 gigahertz, by changing 180 micrometers the membrane. So followed the electrical design, I would like to present to you the mechanical implementation of our sensor for the prototype. We can see here the waveguide with the implemented dielectric resonator here, then the air gap between the membrane and the resonator, followed by the pressure chamber, where we used in our design compressed air. So if we applying a certain pressure, of course the membrane will deflect in the direction of the resonator, and by using different spacers we can adjust the frequency, the pressure range where we want to operate, and by using different thicknesses of the membrane we can also adjust the sensitivity of our sensor. Here we can see the two pictures of the main part of the transducer. Here the waveguide with the dielectric resonators, another perspective view with the fixing screw to fixate the resonator in the waveguide. Here the pressure chamber with our membrane and a mounted spacer, and here the compressed air supply and also the connection for the reference measurement system. At the beginning we used wired measurements to prove the concept of our designed sensor. Here we used a network analyzer to measure the reflection coefficient of our dielectric resonator. Here we can see the pressure reducer, which was used to apply a certain pressure on the membrane surface. And then we used MATLAB and also time gating to extract our informations. Here we can see the measured reflection coefficient by using the wired measurements. We can see that the resonance frequency shifts by already using 200 kilopascal pressure on the surface of the membrane. And what we also can see that the quality factor of our resonator decreases compared to simulation results. And this is the reason due to an introduced air gap between the dielectric resonator and the metal wall of our used waveguide. So by using metal coating of the lateral surface of our dielectric resonator, it was possible to increase the quality factor. And now in the ongoing research, we already received very high quality factors. Now we are coming to the wireless measurements where we want to use time gating techniques. In this graph, we can see the received reflection parameter in the time domain. In the first nanoseconds reveals the clutter from surrounding metal parts in the machine and also from our network analyzer and so on, what they're around. So, and then we can see, starting from 8 nanoseconds, the decay of our dielectric resonators. And this range we will use to extract the resonance frequency of the force sensor. So here in this graph, we can see the already measured resonance frequency peaks of the wired measurements. Here we can see the quality factor is quite low, as mentioned before, due to the air gap between our resonator and the metallic wall. So after this presentation, I would like to summarize the findings in the conclusion. We present a novel monitoring tool concept for milling machines, and this can be used for precise tool lifetime prediction and also for monitoring the milling process. Finally, we present also electrical design, which is scalable for implement more sensors and transducers in one tool to measure the XYZ forces and also the torque. And we did wired and wireless measurements to prove our concept, and it was possible to measure up to 1.5 by up to a range of 1.5 meters. So thank you very much for your attention, and hopefully there are some questions.